Hello, everyone. I am TRAN DAI DUONG from Embedded Systems Design Laboratory, Department of Electronic Engineering, Jeju National University. Today I will introduce to you my research topic, TLB coalescing. Before learning about TLB coalescing, let's first learn one aspect of its usage. The address translation in an operating system, a fundamental concept in virtual memory management. It shows how the CPU operates on a virtual memory space divided into pages, page 0, page 1, page 2, and so on, which are mapped to physical memory frames, frame 0, frame 1, frame 2, and so on, using a page table. The page table maintains a mapping between each virtual page and its corresponding physical frame. When the CPU needs to access data, it first consults the page table to translate the virtual address into a physical address, a process that typically incurs a small latency, 50 nanoseconds. Once the physical address is determined, the actual memory access occurs, adding another similar latency, total 100 nanoseconds. To improve the performance of address translation, hardware designers added hardware called TLB. TLB stands for Translation Look-Aside Buffer. TLB acts as a cache. It will contain frequently used address translations. Every time accessing memory, the CPU will first check the TLB first. If the desired translation is found, the CPU will immediately translate the address and access the memory to get the data. The total time for TLB lookup and memory access is only about 52 nanoseconds, saving nearly 50% compared to the solution without using TLB. However, if the CPU does not find the desired translation, it will access the page table in memory to find the translation, then translate the address, and finally access the memory again to get the data. In this case, the CPU has to trade off an additional 2 nanoseconds penalty compared to the solution without using TLB. But in general, using TLB is a beneficial solution. Now, let's start with TLB coalescing. It is a fact that the operating system tends to allocate consecutive frames. For example, the first two translations have consecutive frames. That is frame n-1 and frame n. Accordingly, we can merge these two translations into one translation in the TLB. To do this, we add a new piece of information in each TLB entry. That is a contiguous field, which represents the number of translations to be merged. This is the idea of TLB coalescing. By using TLB coalescing, each TLB entry can contain multiple address translations, so the TLB can contain more address translations, thereby improving TLB performance even more. Now that you have the idea of TLB coalescing, let's take a look at the research results from the Embedded System Design Lab. The first research result is block contiguity translation, or BCT for short. Traditionally, to support TLB, hardware engineers have to design additional logic blocks that check for continuity and then perform coalescing. We take a different approach, which is to represent the contiguity directly in the page table. The interesting thing is that every time the operating system allocates frames contiguously, using the power of 2 formula, and the address is always aligned with the number of contiguous frames. So this information can be quickly added to the page table with very little cost. Every time the CPU accesses the page table for any translation, it checks the block size field and immediately calculates the starting VPN and starting PPN with very little cost. Thank you for watching, and don't forget to like, share, and subscribe for more insights into computer architecture. If you need more information or want to join our lab, please contact my professor, Jyoungher at email jyoung.her@jejuno.ac.kr.